Thank you very much. Does it work? Okay. I don't want to speak like this, maybe we can put it a bit up, but it's okay, right? All right. So thank you very much for coming, and thank you very much for giving me opportunity to speak. It's an unusual meeting. It's not very large, so organizers took a liberty to give talks. And I'm not thanking Rahul and Uriel because it's coming with, well, it's a privilege, but yes, you have to think about it. And the reason I decided to give a Blackboard talk, there are two reasons. First of all, I don't know how far I can go, and I don't want to rush, so I want to kind of go slowly. And secondly, it's on the border between mathematics and physics, and mathematicians still give Blackboard talks from time to time. And physicists stopped doing that a long time ago. I think last time I heard physics talk on the Blackboard, it was like 10 years ago. It was given by Sasha Polyakov. So anyway, let's start. So indeed, I will speak about Burger's equation, but I'll focus on the transport properties of transport of particles, kind of starting in the initial moment of time, and how they're. So it's a map which map Lagrangian position to Eulerian position at time t. And properties of these maps and how we can address these properties, that's what I will try to address. There are many questions and there are some answers. And also in my talk, I'll comment on many things which Uriel in his talk just indicated, and also maybe what other people indicated in their talks. So I also would argue a little bit with Jeremy, who said yesterday that Burgers doesn't have spontaneous stochasticity. So basically, Burger's equation is important because many things which we hope to prove in Euler equation, they are present in Burger's equation and in extreme way. So it's kind of the same phenomena happening, and we understand it pretty well. And then it's a kind of playground where we can try to understand things in a more sophisticated setting of, or say, different setting of Euler equation. But also equation, Burgers or Kapizet equation or Hamilton-Jacobi equation appears in many statistical mechanical problems of non-equilibrium statistical mechanics, and Kapizet is one of the most prominent of them. So I plan to address several issues like turbulence or turbulence in different settings. One will be with maybe with decaying turbulence, where randomness coming from initial conditions, and then forced Burgers equation. And then I want to emphasize also if connection with Kapizet problem. And finally, if I have time, I will address a problem which fascinates me for a long time: how to define dynamics of this transport map in a complicated setting where you have singularities, shock singularities, but we're in dimension larger than one. So these shocks are not points, but some manifolds. And then since they are manifolds, point by reaching this manifold can actually move on this manifold. And so how can you define this movement of point and how it can be done, especially not in Burger's setting, but in the setting of other Lagrangian system. So let's go step by step. So the basic equation will be for me, sorry, it's indication that I should not go above that. So it's Hamilton-Jacobi equation. So H would be a height function. And then I would have here gradient of H square. So all this will correspond to X variable, and this will correspond to time variable. And this is equal to, let me put it 0 times Laplacian of H plus fxt, which can be 0 and will be 0 in some situations. So this is a forcing potential. It's a scalar quantity. H is also scalar. And that I would call Hamilton-Jacobi equation. Hamilton-Jacobi equation. Or in particular cases, Kapizet equation. Right? And there is equivalent form of this equation, which is a Burgers equation, which corresponds to velocity field, which is, in my case, it will be this gradient of H. And Uriel used to write minus gradient of H, but it doesn't matter. And then equation in this case would be equal to, after this substitution, you get Burgers equation, which is ut plus u nabla u. And again, I have 0 times Laplacian minus fxt, where fxt or the force, so fxt will be with minus sign Laplacian of fxt. And that is Burger's equation. As I said, the potential can be here or not, can be 0, it can be random or not. And again, you start with initial condition. Now, why put 0 times Laplacian? Because we are studying what is called special solution of these equations, which are entropy solution or viscosity solution. So basically, the viscosity is not here, but it's like Cheshire cat smile, it's present. You think about equation where nu is positive and small and tending to 0, and then there is a special solution to this equation. Either this one or that one, they're completely equivalent, these two equations. Of course, if initial conditions satisfy, this is a gradient of some function, and that's what I'll be looking at. Now, you can consider even more general thing. So the gradient of h has a meaning of not velocity, but momentum. And so this is basically momentum p. And this is what is here. It is Hamiltonian in momentum, which is pi square over 2. And that corresponds to Burger's and this Hamilton-Jacobi equation in this situation. But you can consider a more general situation where h on p is a convex function. And then Hamiltonian, of course, it's a Hamiltonian. And then there is Lagrangian, which is function of velocity, which is Legendre transform of that of Hamiltonian. So this is Lagrangian. And then equation would have the same form, but here will be h on so then in this case we would consider h as acting on the gradient of h. And at the very end, maybe I'll talk about this because interesting problem I mentioned about dynamics on the shocks correspond to this situation. All right, so so we want to address both equations. So here is velocity, here is height function, or say potential. For Burger's equation, P and V and U are the same thing. That's coincidence because of the quadratic Hamiltonian, but we'll remember it, but we will not be bothered with this. All right, so what are the properties which we want to address and which are similar for this Burger's setting? And Burger's corresponds to a situation when nu goes to 0, equal to 0, and the turbulent situation for Euler equation. So this is formation of finite size of finite time singularities. This is well understood for Burger's, and which is a big question for Euler and Navier-Stokes equation. And those singularities are shocks. In one-dimensional case, at the points, in multi-dimensional situation, but we will speak very little about it. It's submanifold, I said, but it's well understood formation of the singularities. The anomalous dissipation. It's present here through the interaction, through the merging of trajectories and shocks, and again, well understood. So when you pump energy into system, it reaches equilibrium because you have dissipation coming from this well understood mechanism. Intermittency. Again, well understood. I want to say multifractality, like Uriel wants to have it. But this is not achieved. This is one of the things which we want to achieve, to have situation where multifractality is present. Here, intermittency is bifractal. Bifractality. So there are two scales here. And again, this is well understood. We'll speak about this. And finally, again, rather more mysterious feature of the elder dynamics is spontaneous stochasticity. And I want to say that we'll see situation where it's present in Burgers equation. So all these four features are present, and but they can be studied and understood pretty well. Now the other thing, so let me just say what I'm using, and Uriel mentioned it already. So there is a way to describe this special viscosity solution through variational principle, and so variational principle is the following. Principle, which is known for a long time, goes back to, I don't know, Hopf, but Uriel thinks it goes back to Burgers. Yeah, nobody knows how far it goes. Who invented it? Maybe Euler. Why not? Anyway, so it goes far away, but it's a very powerful tool. It's a way to describe the thing without taking limit of nu going to zero. So immediately say which solutions are, how to describe solution. So I like to draw it normally in a picture. And then this is a time scale axis, and this is x-axis, and we are solving Cauchy problem, initial data giving an initial moment of time. And you want to find solution at particular point x at time t, and say velocity or h, it doesn't matter what you want to find. So what you have to do, you have to consider all curves going down in time, and I call it gamma s, this curve. S here will be from 0 to t. You consider all curves which are regular enough. And you also, of course, want this curve to end up at point x, because it's associated to point x, but that's the only condition. And then for each curve, you can calculate action. So it's action between 0 and t in time of the given curve gamma. And this will be integral of gamma dot square velocity over 2 plus f gamma s ds, integral from 0 to t. Now, then if you calculate this action, this is just a number, and you have to find minimum. So gamma bar 0t x, just starting at 0, going to t, ending at point x at time t, and this is argmin of this thing, of argmin of a0t gamma plus initial conditions. So you take initial potential h at time 0 and take it at time 0, the value. So you have to find curve which minimizes this sum, the action plus terminal payoff, what you get at that point, the value of potential. It's a well-defined variational problem, and if gamma bar is a solution to this problem, it's called minimizer. And again, sometimes in Uriel papers, it's maximizer, but it's different sign of it. It doesn't matter, I write minimizer. And this minimizer brings its velocity. And so solution of the Burgers equation at point x at time t is just velocity of this minimizer at time t. And h function at point x at time t is equal to the action, to this minimum of this, to minimum of this, the exact value of the minimum, not the curve which bring minimum, but the value of this minimum. So it's action, I would say it's action of this curve plus terminal payoff. So that's very convenient set of relation. There is another relation. Actually, so in order to find velocity, you find this minimizer and differentiate it in time. And velocity of this curve is a solution of the equation. The action of this curve is h, but there is another connection because we know that u and h are connected through the gradient. So we know also that if we know h everywhere, we know velocity by differentiating, or if we integrate velocity, we get h. So there is another connection between u and h, right? So also we know
Kostya, why not h is just gamma?
H is what?
Why h is not just gamma?
And what is gamma?
Gamma is what is your last line in your slide.
And H is a scalar, it's a function. It's an action of this curve.
Ah, okay, yeah, I've got it. Okay, so gamma is the whole curve.
Yeah. Gamma is a curve. This is a curve gamma. You consider ensemble of all curve, just ending at that point. So you consider all of them. And there is one of them which is special, which brings minimum to this functional. And this is gamma dot, gamma bar. Right? And,
yeah, got it.
We said what the solutions, but also we know that uxt is equal to gradient hxt. So there is another connection between them. Oh, sorry, but it's not very important for you. So, but thank you. All right. So that's what I need for the future. And now maybe I go to, there is actually variational principles for positive viscosity, but I don't want to address it now. And there is another twist of the story, which is valid only for the Burger's equation, but not for other Hamiltonians, that there is Hopf-Koch transformation, which can transform it to the stochastic heat to the heat equation, linear equation. And then by using Feynman-Katz formula, we can solve this equation. So this is a way to obtain this variational principle. Maybe I'm not going into it because of lack of time, maybe I'll write it later on. All right, now the important feature of one-dimensional Burger's equation and one-dimensional Hamilton-Jacobian equation, KPZ equation, is that minimizers corresponding to different points cannot intersect. That's an intrinsic property of minimizers coming from convexity of Hamiltonian. So whenever two things intersect, you can do smaller one. So it's a very simple property that if you have two minimizers and they intersect, then you may cut this corner and action will be smaller. So minimizers do not intersect. And that's why if you start with a point to the right, the minimizer will be to the right. And to the left, not strictly. So there is monotonicity between of a map. So there's a map basically from Eulerian coordinate to Lagrangian coordinate. And it's not one-to-one map, but it's almost one-to-one map. And there is a map, of course, corresponding map from Lagrangian coordinate to Eulerian coordinate. So I want to address these transport maps. So we have Eulerian coordinate A when t is equal to 0, and x is a given time t. And then there is a map which I denote 0t, which take Eulerian coordinate and transform it to the corresponding x corresponding to A, or inverse map, which take x and transform it to the A depending on x. And these two maps are monotone maps. And that's very important property, extremely important. I think it is basically one of the properties which tells us why many answers which we have at these problems are universal. And so let me draw some pictures. So if I would start with kind of normal initial conditions, so I would start with some initial condition u0, u naught x, which is ux at time 0. Okay, of course, this is a gradient of h naught x, which is a gradient of hx times 0. Then typically what you will see is the following, the map will be the following, so it's a monotone map. So it goes up. Okay, so let me draw maybe a slightly different picture. So what will happen at time t is that many points would have a minimizer. But some points will have two minimizers coming to that point. And that are shocks. Points where there are two minimizers coming to the thing are shocks. So basically it means that the whole interval between shock would have two minimizers, maybe sometimes more, but generically two. And so the whole interval of points in between end up at this point. And on the other hand, if I want to take pre-image of this point, it's not really well defined because it's one of these 2 points. But because of map is monotone, it doesn't matter how I define it at the end. So basically, you would have. If I now want to draw the graph of the function st as a function of a, then I want to draw the graph of this. So I would have a here, and so shocks would correspond to many a's. So that is this interval coming to the same point. And so what you will see, it will be some kind of monotone function which has flat pieces corresponding to every shock. So monotone function with flat pieces on it. That would correspond to a rather regular initial condition. But I'll be mostly interested in a situation when initial condition is regular, but not too regular, which would create many shocks. And so I would be drawing this picture later on for two types of initial. So I'm now addressing what is called decaying turbulence or turbulence, which means that I start with some random initial condition. So I take some initial condition from some probability distribution, and then I solve equation. And then I see what will be the solution and what will be the transport map. And then I take another one and take another transport map. So I will get probability distribution on transport maps. And my initial conditions, I will consider two cases. Actually, more than two cases, but generally basically two. So suppose that my initial H on X is a Wiener process, standard Wiener process. Or in this case, velocity, initial velocity, u naught x, will be just white noise. It is time derivative, x derivative of the Wiener process. It's not well defined, but it is what is called white noise, right? But this function is well defined. It's continuous functions with Hölder exponent 1/2. And second class of conditions would be then you take velocity to be Wiener process. And then H naught is just integral of the Wiener process. It's a function whose derivative is the Wiener process. So that is, of course, much more regular. This function is differentiable, and derivative has Hölder exponent 1/2. This function is not differentiable at all. It has Hölder exponent 1/2. And then for both of this situation, you want to minimize this type of problem and understand the map. And so Wiener process is a representative. I said there are more than two cases. In fact, you can consider generalization of Wiener process, what is called fractional Brownian motion. Brownian motion and Wiener process is the same thing when I consider X thing. So it's another random process, also Gaussian, and which characterized by the parameter which is called Hertz exponent, and I would denote it H on X. And so this is a process which has a stationary increment. So Wiener process is not stationary process, but increment of it is stationary, and so it doesn't matter where you can see the difference between value here and there. And just the scaling of this difference is different. So I would say that if you take x plus r minus x square and take expectation of this for Wiener process, it would be r. And for Hertz exponent h, we r in power 2h. So the scaling is different than for the Wiener process. So Wiener process corresponding to h equal to 1/2 is just a Wiener process. So say Brownian motion. But the behavior is kind of similar. It's also irregular thing with different scaling. And but mathematically, it's very big difference is that this process is a Markov process, and this process is not Markov process. It remembers the past. And maybe I'll tell you how to generate it if you do experiments. So you know that Brownian motion can be obtained from random walk if you scale random walk, right? So you choose ±1 increments. It's a random walk, and then you scale it and you get Brownian motion. Now, how to get fractional Brownian motion with exponent h greater than 1/2? So it has positive correlation. So what you did in the past influence you positively, right? So if you are going in the past more to the left, then it's more likely you go to the left at this moment of time. If you in the past, significant past, going more to the right, it will. So when h is less than 1/2, it's anti-correlated. It's the other way around. That if you were going more to the right, then you will want to go opposite. Anyway, so that's what you do. You have suppose you run your process for a long time, say even infinitely long time, and then you want to decide to go to the right, to the left. Then you take probability distribution of some point in the past with some power law depending on h. So you sample point in the past, and if it was going to the left, you go to the left. If this sample point go to the right, you go to the right. And then this is a game you play. And next time again, you sample another point with the same distribution, go to the right, to the left. If you do this process and scale it, you get fractional Brownian motion, right? And h comes in the probability distribution of how you sample this point in the past. Anyway, so you can replace here, you can put any h here, and you can put h here as well. And that will be more general situation. But you can think about h equal to 1/2, it's good enough for us. It's, mathematically, proofs are much harder and the results are not as extended in h not equal to 1/2, but behavior should be similar. All right, so now I want to draw this maps, which are very badly drawn here, in both cases. Let me start with the case which is a more regular case. So you see, in a very regular case, you have flat pieces, but they cover not everything. There are a lot of points. There's a positive measure of points on A, which are regular, which are not getting swallowed by shocks. And the situation is different when you consider this situation 2. So I'll start with situation 2. So I'm saying that if you look at the a-axis, you have variety of intervals coming to different shocks, and it will be everywhere dense. And the size of shocks in terms of A will be different. There's variety of their lengths. Some of them are large, some of them are very small. And so there's a complement to intervals corresponding to shocks has zero measure, has zero Lebesgue measure, which means zero length. And then you ask what are it's a fractal set. So there is these points which do not belong to shocks. They're called regular points. So those are intervals corresponding to shocks. Maybe I'll say those are regular points. There are infinitely many of them. There are uncountably many of them, but they form kind of counter-type set. And the Lebesgue measure of this set is 0. Why are they called regular? Because at time t, and we start at time this is for everything corresponds to t. There is a minimizer somewhere which ends up at that point. So all red points are reached by some minimizer. Points here do not reach by minimizer. That's the difference. So the set of red points has 0 Lebesgue measure, and house of dimension is equal to 1/2. That's for Burger's case. So for Brownian motion case, for Wiener case. And numerical, now it's proved that if you do this for fractional Brownian motion, then Hauser dimension will be equal to h. And this is rather recent result of George Movchan of 2017. It's much harder. This result was obtained by Sinai in 93, I guess, and then there was paper of Uriel with Shea and Eric Uriel, and then it was paper with Vergasola and Alain Nulez. So that's all in 90s. And the result about fractional Brownian motion is only was proved mathematically by George Movchan in 2017. But it was numerically checked. It was no doubt that it's true by Uriel and his collaborators, and then people knew that it is H, right? So that is so how the map then look like. That is what is called Dayval staircase or counter staircase. So basically, it's a curve which well, suppose it just goes through almost. It consists of steps only. Basically, there is no room for it to grow, but at the same time, it grows. So it means that it grows on this counter set, but almost every element of its length is covered by the flat pieces, and that is what is called Dayval staircase or counter staircase, and that's how the transport map would look in this situation. So again, dense set of shocks, T is fixed. Say T is equal to 1. But you can take any positive T. Dense set of shocks. Each shock corresponds to flat piece for this map. And then it goes from minus infinity to plus infinity because that's basically goes through the whole real line. And this, I'm not stopping here. I'm going down here, down there, up there. And that's how the map looks like, right? And that is in situation 2. And in situation 1, the map, it's even less regular. So it's less regular, but easier to describe. So I believe the picture will be better in this case. Let me denote this. Okay. So now we want to describe situation 1. In situation 1, the minimums of this functional would have an interesting property that if point ended up, so suppose you have minimizer here, that it is very likely that points nearby would come up to the very same point. So it will not change the position of minimizer because basically this is so special place and so irregular function that it's good to be here. So basically every point reached by regular curve would have interval of points here which correspond to it. So what it means is the following, that at time t, so first in terms of picture in time t, you have discrete set of points, t is equal to 1, say. It's a random set of points, and that's a points of shocks. Now, each point of shock corresponds to two curves going down. Since we don't have force, the curves going down will be linear functions. And so that is an interval corresponding to shock. And then next point of shock would come to the very same point, and then you have another interval. And then this one would have another interval, and so on. So let's look at this picture. So what it means, that all points here would have minimizer coming here. So that would be minimizers for all the points. At this moment of time, this minimizer and this have the same action. And after this point, they shift. It's better to go here than there. So all points here will go, and so on. Now, let me stop here a little bit. So basically, there are no regular points. So all points reached, regular points are only those points. The rest is just interval covered by shocks. And all the mass originated at that very point, and it come to this too. So it's extreme form of intrinsic stochasticity. So intrinsic stochasticity means that if you have very little deviation of initial point, then despite that this is very small, at time one, they will be very far away. And the distance will not go to zero when displacement goes to zero. Here, all these trajectories come from that very point. So you cannot say where this point is. It can be anywhere here. So that is kind of what makes sense only that there's a distribution of points which are image of this point. So that is very much, yes.
I have a question. So what's happening at intermediate times in your
Is what?
At intermediate times?
Any time would have the same picture.
Yeah, but
it will be more points.
It means that actually the minimizer are looking like a tree where they merge after a finite.
Absolutely, they merge. They merge.
Okay,
but it's better to say that shocks merge.
It means that you can have different branches, no?
No, what will happen is that, so this is a point of shock, right? And next time, it would be shock above this point. But at a certain moment, these two shocks will glue together. It will be less points of shock. So in any positive time, you will have discrete set of points. The density of this set will increase when time goes to zero, but you have discrete set of points of shocks, and then this decreasing with time, and that's a picture. So always like that. So the transport map would look the following way. So now I'm drawing the transport map. Just consists of, so this is diagonal. So it consists of it's a monotone map which has such graph. So it's what is called piecewise constant monotone map. And that's exactly how the map would look like. And you can inverse map would look exactly the same way, just you take to reflect it to respective diagonal. And that will be true for any potential which is derivative of Wiener process or fractional Wiener process, although this was not studied carefully for h not equal to 1/2. This is the result of Avellaneda and who proved that in this situation, it will be discrete set of points of shocks, and that's it, and nothing else.
Dense?
Huh?
Is this set dense? Or it's
No, this is discrete set. There's a set of shocks at time one is a discrete point field with certain density. They're nowhere dense.
they have a finite density.
Then yeah, they have wider density and they're nowhere dense. So there are no accumulation points of this point. So they're always separated. It is like Poisson process of point process, right? So there are 2 point processes, 1 point process here and 1 point process there, and they're correlated to point processes. And then there is a monotone map which connects them. And that's the main object I wanted to introduce, actually. So maybe I'll not have time for very much of the other thing, but let me just talk about this. So this is 2 different pictures, and then the questions you can ask about them are also different. So one set of questions is the following. So as I said, so you get this monotone map, piecewise monotone map, like this, and it depends on randomness. It depends on the realization of your white noise. So basically, you have random variable which take values in monotone maps. So you have certain probability distribution on these monotone maps, which is inherited from Wiener process. For any omega, you get monotone map. So for any omega, you have 2 point processes and the curve connecting them. So there is a probability distribution of this. So what is a probability distribution? And can you describe it more precisely? Now, the feeling is that all these problems are exactly solvable, actually. And you can find answers to many of these questions, and I'll describe how one can think about it. But in particular, one question you can ask, for example, that here you have velocity field, right? These velocities are velocities of these curves. It's pretty simple. It's a linear function on this interval, and then linear function on this interval, and so on, with jump discontinuities going down, always for shocks. So it's a linear function. Velocity field is a linear function going down, linear function down, and so on. And you can ask, for example, what is a correlation function? So you take velocity at point x plus r times velocity and times x, and take average value of it. Average you can take with either within ensemble of omegas for fixed x, or you can just vary x from 1 to 1 as usual, and then going for different x and then averaging with respect of x. And so this is just function CNR, it's not random function. So what is this function? And you can almost find asymptotic expression for this function, but I just want to say that even qualitative answers to the behavior of this function can be presented. So let me say a few words about this function. So it is non-random function, it's just a function, right? And I'm saying that, so what is the value at 0? At 0 is positive value, it's just a variance of velocity at giving point x. It doesn't depend on x because you have stationary situation. And then I'm saying that it stays positive. And then it goes like that on negative side. And actually, this is a function of C on R. And I'm claiming that for large R, it will behave like e to the minus R cubed. It is very rough meaning of that because there is pre-exponent of there, and there is a coefficient of this R cubed, but it will behave like very quickly convergent here, e to the minus R cubed. Now, how you can understand this? So you basically have to connect velocities of 2 points. And if there are, the only correlation between them comes from the fact that they belong to one interval. If they're within one interval, then they're correlated. If they're with respect of different interval, they're not correlated. So basically, if you have faraway points belonging to one interval, it means that you have very long interval. But it's unlikely to have long interval, because if you have long interval, then the action of different point differs by R squared. Because the kinetic energy coming from this point or from this differs by R squared. So your value of your potential should be very small, so that it is beneficial for you to go there for these faraway points. So basically, you want to say, what is the probability that the maximum of potential in this interval, or minimum, is order R squared? And it's easy to calculate that it will be e to the minus R squared divided by R, because this is the maximum of Brownian motion on interval length R. So it will be R to the minus R cubed. Now, why it's negative? Because why it's negative? Because it's, you see, it is, first of all, if R is small, why it's positive? So you take 2 points, x and x plus R. And it's very likely that they come on the same side of that point. So velocities are of the same side. So the product is negative when they're on opposite side from this point. Then it's negative. So when I is large, it's quite likely that they will be on opposite side, because otherwise the interval must be twice longer, which is very improbable because of the thing. So basically, it means that this will be negative for small r and positive for large r and positive for small r. And so that's the curve. But I think you can calculate it. There are papers where it's calculated. I'm not about that. I'm more interested in the description of what is the distribution of this monotone map. So what is the probability distribution? What we can say about probability distribution of this point map? And now I want to say a thing which I think is important, is that you can think about this distribution of monotone map, piecewise monotone map, piecewise constant monotone map. You can think about it as a fixed point of certain kind of randomization transformation. So what I mean by that? So you can think about this map or this 2-point fields is the same thing. Now, if this point field above is given to you, then you can calculate the potential at this time, right? Now, what I'm saying that I started here. I have this thing, but potential at time 1, which will be hx1, can be calculated. We have velocity, which is a linear function of x. You integrate it to your quadratic function. So potential is a smooth function, piecewise smooth function. It's quadratic function which has quadratic parabola pieces, something like this. And now I solve my Hamilton-Jacobi or Burgers equation for another time interval of length 1. Now I just have to solve it from here to this potential. I don't need to know what was here doing here, right? And that would be some map, which will be just depending on this potential. It will be now simple map. So I'm saying that the map from time 2 to 0, inverse map, can be obtained as inverse map between 2 and 1, and then inverse map between 1 and 0. Right? So this map depends as a functional on the 2-point fields. This map also determined by 2-point fields. You get new map, a new distribution. But because of exact scaling invariance, this one should be equal in distribution to the one we started with. So distribution of this one and this one should be the same up to the rescaling. So you kind of come to a problem. What is the probability distribution such that if you compose this with that and rescale, you get the same thing? And this is a fixed point. And this is translation transformation. Concrete translation transformation, which you can realize on computer if you want to. It's easy. And I would suspect and conjecture that this translation transformation has unique fixed point for giving scaling. And this fixed point is stable. So what it means is that, yes, if I started with exact Wiener process, I would get fixed point. But if I've started from something which behaves like Wiener process, but not Wiener process, then it will not be fixed point. But after a very long time, what I'll obtain after rescaling will converge to the thing. So basically, it's a stable fixed point, it's universal fixed point for the class of maps with giving scaling. And the same should be true for any H. So basically, you'll have one parameter family of fixed point corresponding to different H. And that's what I think is important to realize. I think that there's geometrically defined fixed point equation in terms of the monotone maps. All right. Now, let me change a little bit gear. I don't think I will manage to get to the movement on the shocks, but maybe I can say about KPZ, because KPZ is very similar to this situation. By the way, I want to say that the transformation which transform from this one to that one is non-random transformation. It is deterministic transformation, which take probability distribution of this one and produce probability distribution of that. It's deterministic transformation. So it's a map in a space of monotone maps. And as such map, it transforms probability distribution to another probability distribution. So what I'll have now, it would be similar defined transformation, but it will be now random transformation, kind of more involved transformation corresponding to KPZ. So KPZ would be characterized by forcing term. And normally everybody knows that one have to consider white forcing to be white noise in X and time. But I would consider it maybe in an easier setting when you don't have this kind of difficulty. So I want to do it on a lattice. So what is KPZ? It's the same Burgers equation because it's the same minimization problem, but in a discrete time and in a discrete space. So at every point of this lattice, which I denote by I and T, I will be space and T is time, there is a random variable. And the collection of this random variable for all I and Z1 and T and Z1 is IID. So you have at every point of lattice point of two-dimensional lattice, which you think this is time and this is space. At every point, you have a random variable. And then at time t, large time t, if you want to find solution of your Hamilton-Jacobi equation point x, you have to consider all random walks, and the value of function x at time t will be minimum over all random walks gamma. Now a curve will be gamma. And here you have sum of the psi gamma I from 0 to n. And if you start with some initial condition, if there is some initial condition here, you add initial condition. So it's exactly the same minimization problem. So locality, in previous problem, we had gamma dot square over 2. That's basically just to achieve a locality that you cannot jump very far away, you pay price for this. Here, the price is even more severe. You can just jump only to nearest neighbor. So this is the same spirit. The Lagrangian is different, but it's the same spirit. And the Capizet theory said that it doesn't matter whether you consider discrete setting or continuous setting, the predictions of behavior will be the same. And so what are the predictions? Predictions will be the following, that there are two types of predictions. That so what you predict is that if you look at this curve, which is a minimizer, suppose this is a minimizer, corresponding to that point. Then you can ask, what are the transversal fluctuation of this curve? How far it goes? So by the way, since I didn't fix the endpoint, it can go somewhere here as well. So you can just ask, what are the distance of an endpoint of this curve from point x? And then the answer would be that gamma at time 0, if it originates from point x minus x, will be of the order of t in power 2/3, one of the Capizet scaling. And another Capizet scaling will be what you can say about this function h. And then you say that, again, you can consider any points. You want to say this is sequence of random variables, t increases. So what you can say about these random variables, they're random because they depend on what's here. And you say that it will be constant time t, because you increase, constant can be negative. So it became a linear function of time plus fluctuations. And fluctuation will be of the order of t to the 1/3. And again, you can start with any type of Burger's 1+1 dimensional problem. If your forcing depend on time on x, and there's decorrelation on large times and large t, that will be the answer. Moreover, if I subtract this constant divided by t to the 1/3, the probability distribution will be universal, and we will trace a Widom distribution depending on the setting. It will be either GOE or Gaussian orthogonal, GOE, depending on setting. I'm not going to. But basically, this will have universal feature. Doesn't depend on distribution of this psi if you divide by t to the 1. And this also, if you divide it by t to the 3rd, it will have distribution which is universal and also doesn't depend on it. That's prediction of the theory. Now, there are a lot of success in getting exact formula for function h, which is a height function, and much less success in understanding of geometry of the things. And now that's what I'll address at the moment. And actually, there are more predictions than what I'm describing. It's just very simple part of description I'm describing here. But that's what we want to understand. And all right. And so I want to address it in the following way. Similar to what was before. I want to look on the following object. So I will need a notion of semi-infinite minimizer. So actually here start at 0 and go to point x. But you can start at any time below 0. So you can start very far away from there. So it's good to put the initial condition in negative times and then tend them to minus infinity. And then it turns out that this curve would stabilize. So the curve corresponding to, say, suppose this is 0 and the initial condition is minus t. So what I see, this part of the curve near point 0 will stabilize when minus t goes to minus infinity. And actually, you can define infinitely long curve for every point x. That's not a simple theorem, but it can be proved. So every point would have infinitely long minimizer. Of course, if you start with two different points, at a certain moment they would collide and go together, these minimizers. But this infinitely long minimizer can be defined by any point. And so I want to look at the kind of very long piece of time from 0 to minus t, and then from minus t to minus 2t, and so on, and t will be very large. And then from every point, and now it doesn't matter whether it's lattice or not, because we will be rescaling by t to the 2/3 anyway. So from any point, there is a minimizer going down. And so the red minimizer is going down. And then there is another minimizer which goes with that. And then maybe this one separate for a very long time. So this one, and then this point would have minimizer. And then they separated for a very long time. Anyway, there is a map from here to there. And then there's a map from here to there, and so on. And so basically, the map from here to there have the same distribution as the map from here to there, and so on. And the total map is an iteration of these maps. So you would get iteration of map S from 0 to minus t, and then S from minus t to minus 2t, and so on. And all of this map have the same distribution because they go to minus infinity, but they're correlated. And when, say, I iterate two of them, they would correspond already to interval of length twice as long as before. And now I'm saying that, so basically you can define the radiation transformation the following way. You take this sequence of map, and you produce new sequence of map. So new map will be 0 minus t minus 2t, one map, and then from minus 2s minus 2t minus 3t, s minus 3t minus 4t, and so on. So you iterate couples of them. You again have infinite sequence of map, but any two are iterated. And I'm saying the distribution of this must be the same as distribution of that up to rescaling. And then the conjecture is that there is a unique fixed point corresponding to this procedure, which is determined only by one thing. What is the decay of density of points? Because monotonicity is here, iteration scheme is here, but the density of points, meaning that what will be the density after time minus nt? This is not governed by this procedure. It can be anything. So for KPZ, it will decay like 1 over time in power 2/3, as we know. But in principle, you can have any exponent here. And basically, we're saying that for any exponent alpha, they exist fixed point for this transformation with some universal distribution, which is stable fixed point. So if you start with something which having this density decay, that it converges to that fixed point. At the moment, this conjecture, we can prove it for alpha equal to 1/2 this result. And we have numerical evidence that this is true for 2/3. But philosophy here is the following, that what is important for KPZ phenomena and for universality on the level of concentration points and behavior of transport map is not minimization property, but just property of monotonicity, that monotonicity and decay of density enough to produce universal behavior. And we can have, we saw some numerical evidence by considering processes of coalescing fractional Brownian motion, which do not belong to the universality class of KPZ by any means, because there is no H function for them. But when we do this process, we see the same appearing, the same transport map and the same point fields as for the KPZ. For the here, what I describe is first passage percolation setting, but any other KPZ setting would belong to the same universality class. It's believed, it's not proved, but it's what I'm trying to describe. It's one of the approaches to try to address the proof why we have universality. Basically, philosophy again the following: that there is statistics of this map, and then they are decorrelated, and they are correlated, but the correlation decay, and there is only one way to adjust it in such way that after iteration you have the same statistics. Oh, and this way is a fixed point, and convergence to this fixed point is stable. That's philosophy behind it. So anyway, the message is that it's good to study sequences of monotone maps, random, or like here the maps are random. Here they're random, but they have much less randomness because procedure doesn't require infinitely many random maps. You start with one random map and then apply some non-deterministic transformation. Here you have sequence of random maps. So it's a good to, in order to understand universal features of concentration of points of geometrical objects appearing of KPZ and Burger's turbulence, and objects are like shocks and behavior of shocks and statistics of shocks. One have to study statistics of monotone maps. And this is an interesting problem. I think it's doable. You can get some exact answers as well. And work has to be done. Thank you.
So thank you, Kostya. So are there questions?
Yes. Don't ask me about acoustic waves, please.
There are applications of burgers to acoustic waves.
Thanks.
Yeah. Maybe
Pardon?
here they're relevant. Yes.
Pardon? Are you satisfied now that you are neglecting the PV correlations and diffusion, pressure velocity diffusion in incompressible Euler flow? Are you all convinced or not yet?
In what?
I mean, see, you talked about anomalous dissipation, intermittency, all those things.
No.
But all those things come because you are neglecting the
No,
pressure
no,
velocity
anomalous
correlations
dissipation
and
here,
diffusions.
it's well understood fact.
Pardon?
It's well understood fact that when trajectories collide, and they collide in
Oh,
this
no,
dissipation.
I'm not talking about this lecture. See,
About what?
Jeremy, I think he raised some issue of don't talk about acoustics energy or something. So
No, I said,
yeah.
don't worry.
Okay, not about this. Your lecture about this. Of course, I'm sorry I came late, but you were mentioning, I think, shock location is fixed, fixed or something. I mean,
Fixed now, they're changing.
location of shock. That point. What you
For
were-
giving time, there are special points which are location of shocks, but when time evolves, they move shocks.
Yeah. So
Hello.
okay, shocks move. Okay, it's
Yes, they
highly
move.
unstable. It's normally, I mean, even without viscosity, I think it can be unstable. That is what I mean. The shock location, because shock location is oscillating always in real flows.
It moves, and we
Yeah, it
know
moves.
how it moves. It's
Yeah,
a
but it's not
Rankine
easy to-
Gregorian condition. It
Yeah,
pushes
see,
it.
there is a. I agree. But we can't easily find out how it moves. Yeah.
Yes.
So Rahul has a question.
Pleasure? No.
Leisure.
Leisure.
Hmm?
Uh,
How about Bakhtin and Khanin?
Yeah, that has, I think we have much better understanding now when compared to that paper. That addresses some questions. But for example, what I said here about this, the Avellaneda air situation is not there at all. That's a new kind of twist. And I think it's maybe one can study this more simple transformation first, and then come to KPZ to get certain intuition about this transformation. But this is very doable. This is just you can study.
Uriel has a
I
question.
have a question.
Yes. Somebody online.
I
guess-
have a question. Yeah, Jeremy, online. I'm having a question.
Grisha, I guess.
Yes, Kostya, you mentioned this renormalization group transformation, and that you say that the fixed post is stable. So, do you know what is the C function there? What changes monotonically? Some entropy of what? Of which distribution? Or
I don't think I understand, Grisha, what you want.
you mentioned renormalization group,
Yes, this
which
is
which
what I
produce
call
probability
relation.
distribution as a fixed point.
Yes,
Yes.
yes, there is a fixed point, but what's the question?
The question is, what is C function of this renormalization group? Which
I
quantity
don't know what is
change
C function.
monotonically?
Oh, whether I have Lyapunov function, which kind of
Yeah. Yes.
yeah, no, I don't. It's a good question. I mean, it would be nice if I know this, then I would have simple proof that it's stable fixed point. Now, this is a little bit more involved because there is one neutral parameter. Alpha is a neutral parameter. So it's stable when you fix this density decay. Otherwise, you have one parameter family depending on alpha fixed point. And along this direction of alpha, they're neutral, they're not stable. I mean, you just keep your density profile. So it's a good question. I don't know Lyapunov function for that, but in a sense, when we did it for alpha equal to 1/2, we can describe fixed point exactly, and that helps to prove stability of this fixed point. So this fixed point for alpha equal to 1/2, it is it's getting by time-one map for coalescent Brownian motions. And then you can prove that you converge to this, but Lyapunov function, I don't think. I mean, we don't have it. It would be nice to have it.
So Uriel has
Thank
a
you.
question.
Hello, yeah, it's working. Yes, as you know, of course, for the case where the velocity, initial velocity is Brownian, it's been known for a long time that there is a huge accumulation of shocks. There are devil staircases, etc. Now turning to the case where the potential is either Brownian or some variant thereof. We know that in the Brownian case, there is no accumulation of shocks. The evidence, the numerical evidence that when the initial data for the potential is fractional Brownian, there's also no accumulation. Do you have any evidence mathematically that this is so?
Well, I would say I have no doubts that it is so, but so you see, Uriel, I think that what is important here is not really statistics of these initial fields, but the fact that they're not very regular, so that they oscillate. And if they oscillate, then you will get this property. And even the fact, you see, there is a little bit of strange thing with if you take velocity field being Wiener process. And somebody would say, why it should be Wiener process? Wiener process is not stationary, and velocity field should be stationary. I mean, why it should be non-stationary? You can make it stationary. If it's locally fluctuate like Wiener process, that would be enough to get the picture of fractional Brownian, of fractional behavior in case of velocity field being Wiener, locally Wiener, or in case of potential being local Wiener, then you have similar to, it's just irregularity. So for example, I said that Villaneda and Air considered Wiener process, and I say, let's consider fractional Brownian motion. But again, as a potential, it's also not stationary. But if you want to have stationary, fine. I mean, take Airy process. It would be stationary locally like Wiener process. And I'm sure behavior will be very similar. So the fact that non-stationarity is not really important.
Yeah, I understand. But at the moment,
no mathematical results.
Wait, in the paper, which many authors, including you, this is not mentioned.
Yes.
Perhaps you should mention it.
Yes, yes.
So any other question? Okay, so let's thanks Kostya again.